All right, guys, let's continue. Apologies about that. So we're beginning transformations. Now, we're going to be looking at all the transformations that are going to be covered in your syllabus, and most of them, almost, I would say almost all of them, are going to be carried forward from IGCSE as well, and we're going to be looking into that. So it's not unfamiliar territory with for you. Um, in terms of being completely blindsided by the topic. Before we begin with this, we're going to begin with, like, let's just say that let f of x be a quadratic equation. All right, let's just play pretend for a minute here, and let's just say that f of x is a quadratic equation, because most of the transformations that we're going to go through, they're going to be, if I feature only quadratic equations as well, that is going to be well enough to give you guys the idea. The reason why I'm not using linear equations on transformations is because they're not going to be very clear for you to understand in order to explain the shift in the graph. Why we're using quadratic equations? Because for a curve, it's much more easier for me to show you the shift wherever the graph has gone. But it's a bit more difficult for me myself to show you the shift in the cubic graph. But so that is why I'm using quadratic equations. So if you're, let's just say that you're posed with the question that you get a cubic equation in the exam or something like that. Still, a cubic equation, if you break it down, isn't it two parabolas as well? Like it's two curves. If you break it down from the middle, it is still two curves. So there's always an element of a quadratic equation in it, that hence we're using it. Let's continue forward. What we're going to have is that we're going to continue with what you may call um the graphs. So also, hmm, we're going to need to draw the graph. So let's just say that. Mhm. Yes. Any questions from anyone?
Mister, could you repeat? Because my internet disconnected. So,
Parsa, we've just, we're going to pretend that, f of x is a quadratic equation. I'll explain what that is.
okay.
Beginning with this, let's start off with the fact that, f of x, y is equal to f of x is a quadratic equation. This is a quadratic equation. Let me just try and do that. So let's just say that y is equal to f of x, and this is just a very generic version of that graph. Now, what if, one scenario states that y is actually, wait, we have something being multiplied to the entire equation, or something is multiplied not with one individual aspect of the equation, but with the entire equation. Something is multiplying outside the bracket of the equation. All right, let's just assume that the equation is placed in a bracket and something is multiplying outside. This right here, this sort of like multiplication of something to the equation and outside increases or decreases. Now, this can be two cases scenario for this. Either this will increase or decrease the amplitude of the curve. This is going to increase or decrease the amplitude of the curve. Now, this information is going to be critical in understanding when we move on to trigonometric graphs. This information, where you're going to see consistent waves. So when we transform those waves, you're going to notice changes in amplitude and changes in frequency and stuff of that sort. Now, you're multiplying something to the entire equation. there's a is being multiplied to the entire equation. A is just, let's just say, a variable. You can change it around. But obviously, there are, for now, there are going to be two possibilities of it. What are those two possibilities? Let's see. If a is greater than 1, obviously it's common sense that a is not going to be equal to 1. All right, it's pretty much common sense that a is not going to be equal to 1 because you're multiplying with 1. That's not going to have any effect. Moving forward, if a is greater than 1, you're going to have what we try to call a vertical stretch. Now, when I say the terms, now these are a few terms that you might find confusing at first, but we'll try to decode them. This is called a vertical stretch for some reason, that you're trying to stretch it vertically. What do I mean by vertical stretch? That imagine I'm holding onto this graph from its ends, and I try to squeeze it upwards. Sorry, I try to stretch it upwards. I try to pull it from towards myself. So what is happening? The graph is being stretched upwards vertically. Now, if the graph is being stretched upwards vertically, what is going to happen? That the entire graph is just going to shift inwards. It's not going to lose its position. It's not going to lose its position. The only movement that you're going to see is of the graph moving inwards. Now, if we were to showcase movement, this is how the movement is going to take place. I wanted to show dotted lines, but apparently the pen's too thick. Wait, can I decrease it? Oh, wow. That's what happened. All right. You have moved inwards into the graph. That's what's called a vertical stretch. Secondly, now another scenario could be for now. I'm referencing for now again and again because we're going to look into transformations which involve negative numbers at the end. What if a is less than 1? It's a smaller number, it's less than 1. But I have said that we're not going to be discussing negative ones right now. So, make it greater than 0. Obviously, it cannot be 0. We don't want to finish up off the entire equation. So, what's going to happen? Again, you're going to have some sort of vertical action going on over here, but it's going to be some sort of vertical squeeze. Now, what do I mean by vertical squeeze? Just as I said that I'm stretching it up vertically. Vertical squeeze would mean that this is vertical, right? And I'm squeezing it down. Now I'm pushing it down. So what is going to happen when you push this down? Obviously, it's going to bulge outwards. It's going to move outwards. And when that happens, your graph is going to look a bit more, you can say, um, a bit more, you could say fatter, even. Your graph has just expanded a bit more. And if we were to show the movement of the graph, obviously your original graph is your red one. So this is going to be your graph, and it's going to be like this. So this is your movement, and this is your movement. Now let's do something fun. Wait, just a moment. I'll explain to you what am I doing. I'm again going to my, you guys must think that I'm obsessed with it, but I'm not. It's just a very convenient app that there is. So I've opened up Desmos again, as always. What has happened with Desmos now? I'm going to showcase the entire thing over here. So I'm going to just say y is equal to x squared. All right, just a generic version of quadratic equation. I'm going to put y is equal to a x squared. And over here it says, if you guys use this app, it says add slider. I'm going to add sliders, and I need to add, like, I don't know how to add multiple sliders, but hopefully I can. I can figure it out. Aha, yes, I can. Mm-hmm. Yes, I think I can. Aha. All right. Wait. How do I add one more slider? Mm-hmm. Over here, you guys can clearly see that the value of A, I've written over here on the Desmos app, that I've used y is equal to x square as my generic graph, which is written in blue, which is actually, okay, which is written in red, y is equal to x square, just as a like over here. And I've used another graph. I've used a transformation where something multiplies to the entire sort of quadratic equation. When something multiplies to the outside and to everything, what's going to happen is, if that value is greater than 1, see what is happening to my graph? As I'm getting the value greater, I'm going, and the graph is, what's happening to the graph, guys? It's squeezing inwards, just as we said over here. That if the value of A is greater than 1, you're going to have a vertical stretch. Why? Something is pulling this upwards. You're stretching it out. So the bands come closer to each other. But
Because Mr. Like
hmm
for X, it's like against the logic. Like for example, if I have Y equals
hmm
2, like for example, I have f of x equals x squared and f of x equals 2x squared, it would be
yeah.
a horizontal stretch by scale factor half.
Hmm You're okay. You're talking about it. Okay, I understand what you're talking about, Basa. No issues.
Whereas if it was f of x equals x squared and 2f of x equals x squared, it
Hmm
would be vertical stretch by scale
Yes,
factor.
sir. You're absolutely right. The transformation Parsa is talking about, he's absolutely right, Parsa, that it's going to be f of, this is how I'm going to denote it. Whenever we're talking about horizontal stretch and squeeze, we're going to be talking about this. But for now, I just want to illustrate this point that when the value of A becomes greater than 1, the graph sort of vertical stretches or goes inwards, you can say. And when I go between, I'm not going to go between what you may call, um, I'm not going to go less than 0. I'm not going to go negative for now. You guys can clearly see that the graph moves outside. The blue graph is the new transform graph. So you guys can clearly see that, it can move outside. Is this clear? So let's just say that 0 and 2. All right. So look at the movement of the graph. When it gets greater than 1, and when it gets less than 1, you can see, notice the graph how it's moving. Okay, like this. Wow. Is this clear, guys? Nofal, is this clear? Any issues with this, Nofal?
No issues.
Oh, let's just stay it over here. Okay, now let's move on to what Parsa was saying. Parsa was trying to describe that, what if I have some sort of, again, y is equal to f of x is being used. hmm Over here. And what's happening to it now? Let's see. So when y is equal to f of x, where f of x is considered a quadratic equation is used, but a transformation happens such that, you're multiplying something with x alone inside. Let's see how that happens. F of ax. When that happens. All right. When something is not multiplying to the entire equation, something that is not affecting the entire equation, but it's affecting what you may call, um, inside the equation, when something's multiplying with x. All right, with something is multiplying with x squared or something of that sort. Whenever you have something multiplying with x inside the inside the equation of the curve, but it's not having an effect over the entire thing, then you're going to have what you may call um first off, what we're going to see is that what sort of effect is it's going to have. It is going to increase or decrease the amplitude of the curve. The amplitude of the curve. All right. So it's going to increase or decrease the amplitude. Oh, apologies. Wait, sorry. It's going to increase or decrease the frequency of the curve. Apologies. The amplitude is increased. I had that in mind. I was looking at it while I was writing it down. So the increase or the decrease in the amplitude is going to happen when something multiplies with the entire equation. Whereas if something multiplies with only x, you're going to have an increase or decrease in the frequency of the curve. Now, again, two possible outcomes you can have. Like this, what's going to happen over here? Let me write it down right here. Whether a could be greater than 1 or a could be less than 1. Now, Parsa was absolutely right in telling us that when a is greater than 1, there's a horizontal squeeze because now it's something it's multiplying with x. So it's a horizontal squeeze. And if a is between 1 and 0, it's less than 1, that means it's a horizontal stretch. Almost like the opposite thing that's happened. So it's going to behave the same way. How is it going to behave the same way? But we're going to look at it from a different perspective. We're going to be looking at it from a horizontal perspective. All right. If I say that, there's a horizontal squeeze, that means this is the graph, the original one, and I'm squeezing it horizontally. First, if there was a vertical squeeze, I would have done it like this. But now it's a horizontal squeeze, so I'm going to go like this. Because that is the case, the graph is going to become, sort of like be squeezed inwards. So it's going to take place like this. So I can just simply, cheat a little bit. All right, like this. Clear? And at the same time, if it's a horizontal stretch, that means horizontally, I'm going to pull this guy apart. So it'll become a bit more wider. So it's going to become this guy. Clear? So it's going to be like this. Is this clear? Nofal, is this clear?
Yes, sir. Clear.
Yes, Mr. It's clear.
Well done. Now let's see what over here. I'm afraid I'm going to have to change the values as well. So y is equal to, I need to make up something. Let's just say that x plus 2 whole squared was happening. And this, where is the equation? Okay, this is the equation of the graph, guys. And if something is multiplying to the outside, like for example, if there's any sort of, if I put a slider on there, so x plus 2 whole squared, right? If I'm not wrong. Now, if something was happening to the outside, you guys will notice if I increase it 1, vertical stretch. If I go less than 1, vertical, the blue graph has gone a bit wider than this. You guys can probably not see it to that extent because we are zoomed out, but that's how it is. Now, what I'm more concerned with is not this. I'm more concerned with when something only multiplies with the x inside. So it's going to be under root 2. Oh, not under root, sorry. 2x plus 2 under bracket, I wanted to say. Whole squared. Not 2. Why am I doing 2? I'm a bit crazy. And it's going to be like this. Yes. Now what's going to happen is that I'm going to add another slider over here. It was using the previous one. Now you guys will notice that it's perfectly overlapping when the value of A is 1. But when I make it, the value of A becomes positive, you can clearly notice that my graph is being squeezed horizontally. Like if you're pulling in from the sides, if you're going in from the sides, it's been, pulled in. And when I go for greater than 1. But if I go less than 1, you guys can clearly notice that my graph is expanding. All right. That's the difference that happens. Is this clear, guys? Anything that anyone does not get, let me know. Horizontal squeeze, horizontal stretch. No, that's kind of hypnotic, to be honest. Any issues with this, guys? Anything that anyone doesn't get?
No, sir.
Hopefully not.
No, sir. No issues.
Oh, all right. Now, let's look at. I'm afraid I'm going to be copying the same type of graphs because I don't want to draw new ones. That's what it is. So let's just say that, there's the equation is again, I'll copy that down again. Y is equal to f of x is equal to, let's just say that, what if you add something to the equation. We're done with multiplication. Let's do addition now. So for example, when that happens, what is going to happen is that was f of x. But you're adding something to the entire equation. All right, it can be plus or minus a, adding or subtracting, whatever it is. You can do that both. When that happens, you've got two scenarios again. One is when you're adding a, that is going to show you, and always this entire sort of plus minus into your entire equation. Like your entire equation is going to be what you may call, when you add or subtract something to the entire equation, it's going to be movement along the y-axis. So it's going to be movement along the y-axis. Keeping this in mind, if you're adding something to the entire equation, if you're using plus a, what's going to happen is that simply you're going to move in the positive y-axis direction. All right. So you're going to move in the positive y-axis direction. How are we going to do that? I need to duplicate this. So I don't like this. So I'm using green, right? This one's I'm using. Okay. That's your curve. Nothing's going to happen to the curve in terms of expansion or contraction like we experienced above. It's not going to move outwards, inwards. It's not going to have some sort of vertical stretch or squeeze. It's just going to have the entire curve is just going to pick up and move upwards. So if you're adding, it's going to move in the positive y-axis direction. Where is that? The positive y-axis direction is obviously upwards. So it's going to move upwards. Your entire curve is just going to be lifted upwards like this. But the main question that you guys should ask is, how do we know how much to move? You're going to move upwards. Just a moment. You're going to move upwards. How much you're going to move upwards? A units. Whatever the value of A was, that's how many units you will move upwards. So you're going to move in the positive y direction a units. All right, whatever it was in terms of a units, you can say. So let's just say that a is equal to 5, for example. You're adding 5 to the entire equation. So what's going to happen? That you're going to shift your graph up 5 units, move in the positive y-axis direction in terms of a units. All right. Now the second question that comes to our head is the fact that negative a. So it's going to be, what is going to happen? Obviously, if you're using the opposite sign, you're going to have some sort of inverse movement. Just copy this exact thing down again. And what I'll do, oh, wait. It is going to move in the negative y-axis direction in terms of a units. How is it that going to happen? Take this graph, duplicate it, color it. When you color it, it's going to be, I'm going to put it down because now you've moved negative units. So it's going to be like this. And just simply going to be like this. Okay. All right. That is how you showcase movement along the, just a moment, let me align this, the entire thing. So you're going to have movement along the uh, y-axis when you add something to the entire equation itself. But let's see this. So I'm going to keep this, and this time around, I'm going to add something to the entire equation. Let's just add a and add slider. So if I add something to the entire equation and whatever value, you can clearly see my graph is moving upwards. Oh, my graph is moving upwards. Wait, let me put it from between 0 and 10. All right. Now let's see. You can clearly see that whatever unit of A is, my entire graph has been lifted upwards by the exact same units, whatever the units may be. And at the same time, if I put in negative A, you guys can clearly see that whatever value of negative a is going to be, my graph has moved downwards. That's the movement of the graph. Is this clear? Uh,
Yeah,
Nufal?
yes, Mr. Clear.
All right. Okay. So, Parsa, that is it going to be it for today. We are going to continue this on Saturday now. All right. Until then, as always, Parsa, keep smiling. Bye bye, Parsa. I'll see you on Saturday.
Thank you, sir. See you.